Alright, off we go.
Can we just not about Schrodinger?
Oh, I can use my surf
Throw him out and just not work.
Why do you guys hate on him?
He was
I
really
don't
neat
know
guy.
him.
He was kind of crazy. He was really weird from the little bit that I read about him. But basically, if I remember the story correctly, he just went off to a cabin or something like that, like hole-in-the-wall woods, and then showed up later, a couple months with this equation. Out of nowhere. That's kind of how that went. And the funny thing is, the way we introduced this is pretty much the exact same way. All of a sudden, we ran an equation on the board, and we just spent the next 3 months talking about it. So it's not terribly different. All right, let's summarize what we did last time. Last time we talked about the wave-particle duality of matter, and we came up with two main equations. That the momentum can be expressed as h bar k, and that the energy can be expressed as h bar omega. And we call these things the wave-particle relations. So we say that because we've got an energy of the particle is a function of the angular velocity or angular frequency of the wave, and we've got the wave number related to the momentum of the particle. So that's why it's kind of going back and forth between those two. All right, now we're going to rewind to 2212 and hopefully what was in 2202 to talk about a wave function. Wave function. In that, we magically wrote down a wave function. We said that the amplitude of your wave at any point in space and time is equal to this. And then we ran around and around and around talking about this for a long time. We said A here is the max amplitude. So whenever this over here, the sign of this becomes 1, then we're at max amplitude at that particular point in both x and time. Now here we have the wave number, and here we've got the angular frequency, or angular velocity, whichever one you want to describe it as. Okay, so something else that's kind of interesting about these numbers, the wave, the spatial frequency or the angular temporal frequency. Actually, let's put that on there. This we call spatial. That's the K. This guy is known as either angular, or we call it the temporal frequency. It is a frequency, so it does give us information all the time. You got to remember that the radian is a false unit. All right. Now, did you have this stuff? You had to have that equation, I hope.
It's not ringing a bell yet.
Okay, so we would say, for example, when we had a spring, the spatial, we would put the spring constant in here. It was slightly different because we didn't have our omega t was a function of that. But k was a function of the wave itself, as was omega, and then you had a certain amplitude depending on how far you sent the wave. And you could solve for your wave height anywhere. And then we could also get information out of our phase constant out of this. A little bit, maybe. Well,
like photon stuff is a wave. Like it's only going, it's still going in one direction. It's only going up and down, and never goes side to side at the same time.
No, we usually, that's an interesting point. When we talk about it in space, we usually will solve it as a one-dimensional thing, but to say that it is only going in a wave in one direction is not true. So it could be going one direction, and it also could rotate, so that it starts going in another direction. So as it's oscillating in X, it can also necessarily be oscillating in Y.
So does this give the
Now we can always simplify it in general until we get to chapter 7. We'll simplify everything as being one-dimensional. Here we go.
Does this give the particle in the box then, or is this completely different?
Yeah, eventually. That's until chapter 6, I believe. But we will have particle in the box here shortly. Is the cat dead or alive in the box? All right, so we've got a wave number here. And we've also got our angular frequency here, which we said was 2pi over t. So, neat thing, if we take W, or omega if you will, and put it over K, what do we get? We're going to end up with alpha, or lambda over T. Now, lambda is what units? Has what units?
Meters.
Meters. It's a wave. What about T? What does T stand for? What means period? Seconds. So we got meters over seconds. We have the wavelength divided by the period of the wave. This necessarily is the same thing as saying we have got our change of x over our change in time. This gives us our wave speed. And we talked about this a little bit yesterday, or yesterday being Tuesday. The only difficulty with this is that Nia has a movie camera. Taking notes isn't important. Can you reach from there? I can go back. That's you.
Okay.
Awesome, thanks. All right, so the wave speed. This is the speed of the wave, not necessarily of the particle. Okay, which is confusing. All right, but we'll get to that a little bit more today. Next, where on earth did this come? We just made this thing appear out of thin air in 2212 and said that, okay, this is the wave function that solves the wave equation. And we don't really get into the wave equation, largely because this happens right at the beginning of 2212, and most people haven't had calculus 3. To do that, you need partial differential equations of order 2. So the full version of the actual wave equation is going to be this.
Wait, is the calculator free for this class?
Yes.
Okay, sure.
I do believe so. It better be anyway. All right, so this is a second order partial derivative. And the good news, Kyle, is we're only going to be dealing with derivatives, no integrals. And I will walk you through how to do all these. We're going to take the derivatives slowly. All right, so this is the wave equation in its giant form. With one exception, it's supposed to be v squared. So velocity squared, and this is kind of a neat thing. If you guys end up taking Simmons' classical mechanics course, you will look at this equation in detail. This is actually what governs a wave. Okay, for a wave to be in existence, it says that the velocity squared has to be equal to the second derivative of the position. Multiplying these two necessarily must be equal to the second derivative of. Why is that saying y? Sorry, I'm not paying attention. You're a hypersensitive like him.
So, these are legendary?
Allergies or just,
Allergies, probably. Okay, I'll put tissues.
See, you're smart. I should script out else. All right. So, other mistake. This is supposed to be temporal. This is supposed to be your time derivative. I just wrote y. Would you ask though, Dave?
Still squared.
Yes. This is well. It's the second derivative thereof.
Yeah.
Instead of winging it, pay attention to this. I got it right. All right. So, and this does kind of make sense. This is saying that the change in position that you have, okay, the rate change of position, which is going to give you the slope of the slope, has to be a function of also your time. In other words, you can't have, like on a string from here to here, you can only have certain wave patterns that are going to go across and back. Especially when you end up with standing waves. There are only certain standing waves that you can have in between there, here and there. Certain wavelengths that will allow you to have standing waves. And that's all that basically says. Now, what did these two things have in common, or have to do with each other? Wave equation. And I'll leave this for classical mechanics, but what goes in here is necessarily a solution for the wave equation. So we have to find something, some yx of t, namely the wave function, to go in the wave equation to satisfy this. This is what is required to be a wave. Now we need some sort of function that will fit in here that works. And if you spend the time to throw that equation into here, you'll find out that this is in fact true. That the second order spatial derivative is equal to the second order time derivative.
Please don't make that our homework.
No.
Yeah.
He thought about it. That's what the story's doing.
Well, your homework is not terribly dissimilar to that. You only have one question on your homework. Should take you less than 5 minutes, though, because we're going to do the same thing with a different equation.
Should.
So it's not.
So,
It's 5 hours.
Well, us undergrads
I'm
spending
smart.
2 or 3 hours to try to figure
Not
out.
smart people.
Speaking of, looking at the guide for the homework, where did we go wrong on that? Did you guys even look at it, or you just throw it in?
You started
I
talking
can't even
about
remember what I put on the homework.
So it doesn't matter, right? I realized
I'd
I
have to
shouldn't
see
be
my
able to give you
homework.
homework. Yeah, I didn't quite get all of it.
this. Wait, what happened?
I didn't want to give. Okay, I was just curious. You guys said that that one was a tough one. That's why I was kind of curious.
We haven't
done
done
it wrong.
You did this 2 minutes ago.
What?
Yeah, we did. Yeah, we did physics.
Anyway, all right, moving on. So, going to erase this. This is the wave equation, and over there is our wave function. We're going to have to do the counts and go back over to the wave equations. Now, it turns out that the way to describe matter waves is not terribly different. The wave equation is not terribly different. The wave equation is this.
This is pretty bad for me.
Yeah, not difficult at all.
This is the Schrodinger equation.
I know what
Oh, hey, I wrote
are.
Hey, I
All of
recognize
it
that.
is caloric. You know what more things than that are in there. Alright, here's our Hamiltonian over here. So we've got h bar squared over 2m, m being the mass of the particle. We have the second derivative of this psi x of t. Psi x of t is now our wave function. Okay, just like we had the wave function for simple strings and waves and things like that. Now at the particle level, we can say the Schrodinger is our wave equation.
Is that I?
This is I, yeah, that's hard to see. I each bar.
Choice.
Okay. Now, there's lots of things that are probably not happy about this equation from the student's point of view. It looks scary. Kind of is scary. First of all, it would be nice if we sit there and derive this and figure out where this came from. Impossible. Impossible to derive from first principles. This is perhaps the most difficult part of quantum mechanics, or even in this course, modern mechanics, is just accepting that this equation appeared out of nowhere.
I can accept that.
Yeah, okay.
I can-
And
Not
just
that
run with it. And again, when he came up with this, he looked at all the data, everything that ever had been done, and tried to find an equation that would fit it. And he did. And ever since then, everything we've done has fit this equation. There's no way to derive it. This, as far as we can tell, is first principles. That all particles are governed by the Schrodinger
So you
equation.
tell me he literally just poofed this out of thin air.
Yeah, he pooped this out of thin air pretty much.
He was abducted,
It
wasn't
was- What?
He was abducted, wasn't he?
Aliens? Could be. Very well could be. Alright, so that's the first thing. Now, the other thing is there are imaginary or a imaginary number in this. And the general response from students is boo this. Insert other profanities that are probably a little bit stronger. Now, if you guys don't remember how to deal with imaginary numbers, I should refer you to Appendix K.
Close your eyes and tell yourself you're not here.
Exactly. All right, what is the definition of I?
Square root of -1.
There you go. Okay, so I squared, therefore, is equal to -1. So that generally violates most math principles, except it doesn't for I especially do that. So if you want, you can go review that. Now, why do we have I in there? Doesn't that just make everything more difficult? In a way, it actually makes it more simple, and I will try to explain. Alright, the imaginary number, or making this entire equation have an imaginary part, literally doubles the amount of information we can store. Any information that is sitting in an equation that has an imaginary number into it now has both a complex part and a real part. Okay? It literally does double the amount of information. Now let's go look at wave equations for something else. Alright. E and M fields. Okay, and you take my E&M course to get more into this. When we talk about the wave equations for E&M fields, electricity magnetism fields, or E and B fields is usually the way it is, these are given as two separate equations. Everything that we've set up here is very similar. It's not a Schrodinger equation, but we're going to have the wave equations, and we'll have Maxwell's laws that dominate what goes into those. But we come up with two separate equations, which, to be honest, we could do here with the Schrodinger equation. The reason we do that is because we would like to have something that describes the electric fields separate of the magnetic fields. Okay, but there's no reason that they couldn't be written as one complex function. We could write E cross B fields, electricity and magnetic fields, as one equation with complex notation. Now, it's not traditionally done because we have a general grasp of electric fields and magnetic fields, so we keep them separated. Now, as far as the Schrodinger equation goes, we have no concept of what it is separated or combined, so there's not really a whole lot of advantage to separating them. In the event that we did separate them, it would look like this. There's the first one. The second one is going to be sorry. There's a whole section in your book that goes through the Maxwell equations and talks about E&M. I wanted to gloss over that because if you haven't had E&M, just seeing the whole list of equations, I think I thought was kind of confusing. But it has Ampere's law and it's got all of them on there. You're welcome to go through them. Perhaps I should introduce this after I said that. So I can write this now. This is identical to, has the same information that this equation does up here. Now, where are the differences? Okay, here's psi 1, psi 2. Psi 2, psi 1, and then the negative sign. That is the only differences. Now, if these two equations add up to be the exact same thing that this equation does, how do we put them back together? How does psi of x of t relate to psi 1 and psi 2? Well, it turns out that if you take this, you can say this is equal to psi 1 x of t plus or imaginary I multiplied by psi 2 x of t. So we can either deal with one psi function that has both a real part and an imaginary part and put it into one version of this equation, or we can have two equations that there's no imaginary part in the first place. Now, when I was relating back to E and B fields, this is not, actually I'll talk about that in a second, I guess. Okay. So we're just going to stick with the one equation. That's what's traditionally done, and it simplifies things, and pretty soon you'll get used to dealing with imaginary numbers. It's not the end of the world. And we erase this stuff right here. This is, if you're looking for this, this is not in your book. It's actually listed in the back of your book under one of the example problems. Example 34, maybe. So you can find it in your examples. Or not examples, your homework problems. Don't worry, I'm not assigning this homework. Okay, so what do we do with this? How useful is the wave function in the first place? Arguably, none. It serves absolutely no purpose. The wave function is not useful until you take the square of it. Okay? So if we take the square of this, then that becomes something useful. Now, what happened with the original wave equation that we had for particles on a string, or actually locations on a string, etc.? When we squared that, what function did we get?
Like amplitude.
We started with amplitude, because that's what here was. Intensity. We get intensity. Intensity actually has more information than amplitude, interestingly enough. Now, intensity is actually gives us, we'll see here in a second, the probability density. Intensity is the likelihood of finding the particle there. Amplitude, we think about amplitude. What the heck is amplitude? Amplitude is just a function of the function, if you will. It's a descriptor of the function. It has no real meaning. That's a little dangerous to say, but intensity is where we're interested in. So we're going to try and go for our psi squared, because that's what stuff is interesting. That will give us our probability density. And I'm going to write this down. I like this definition slightly better than your book, so we'll go with it. The probability of detecting particle in package. Okay, we'll stop there for a second. Probability of detecting the particle within its wave package. This is my own terminology because it's a mix between what we saw on YouTube and what we were talking about before. So in other words, the particle is moving back and forth in this wave. We're trying to find it. Where is it? So it's somewhere in this wave package. So this is the probability of detecting the particle within its wave package. Per given length. I'll put this in parentheses for now. Given length. Proportional to the square of the wave function. So that's how we go about finding the particle. That's why this is useful. And we want to pin down where a particle is. Now we're going to find here in a little while that the particle is not necessarily evenly going to be in all locations. It is more likely to be in some locations than others. And that's where this becomes handy. Our probability of detecting the particle within its wave package per given length, this part in the parentheses I'll explain here in a little bit, is proportional to the square of the wave function. Turns out that when we start looking for the particle, I will ask you things like this. David, you were asking about the box, right? Particle in a box. I will ask, and we'll talk about the infinite well and the finite well. You guys have probably heard these terms before and not really know what they meant. You know what they mean. You guys did this, didn't you? You guys actually blow through infinite well pretty quickly, don't you?
I have to see it.
No worries. It turns out that I'll ask you things like what is the likelihood of the particle being in the first third of the box, the middle third, the last third, things like that. We will always ask.
That's my response. That's my response to that.
Don't be rude. All right. Because what you're going to say is I'm not going to say what is the likelihood of finding the particle at exactly point A. Turns out that that doesn't really mean anything. There's a couple of reasons that doesn't mean anything. One, what we're going to talk about next Tuesday is the Heisenberg uncertainty principle. The probability for finding anything at any one location is 0. It can't exist at one location. So what we have to do is we're going to have to talk about a range. Okay. So when we start looking at this, we're going to say per given length. So the probability density is going to say it's a probability per meter. Okay. That we expect to find this. And you're going to say, okay, the probability within this 1 nanometer, we expect to find it here, within a certain range. All right, now, to square this, we have this function right here. Okay, so when we end up squaring this, what we're going to end up with is a square of the real part and a square of the imaginary part. And this is also true for E and M stuff. In E and M, if we take the square of the two ways, we get E squared plus CV squared. The magnetic field, the speed, and then we've got our E squared term over here. Now, if we actually take our fields that go into this, this is going to give us our intensity, okay? Our electromagnetic intensity, the location of the maximum electromagnetic intensity. Again, you can read the book if you want another session. I didn't want to get buried in the it's identical to what we're doing with the particle and the wave. So once you get to classical mechanics or you get to E&M, hopefully that'll make those courses really easy. Where's that? If we can struggle through and make sense out of all of this stuff. So now what we want to do is we want to take the wave function and we want to square it. Let's figure out if we can do that. All right, I'm going to erase most things. I'll put the wave function up there. And you'll note that I'm leaving the wave, leaving the wave equation up there and the wave function, because I don't have any functions for this yet. All right, so in order to square this, we need to square both the real part and the imaginary part. So I'm going to put this as RE psi x of t squared. I'll follow your book's notation relatively closely, with the exception that I'm going to put an I here. Your book accidentally at the top of your page here puts a 1 instead of an I for the imaginary part, so it's 1n instead of IN. I thought that was kind of an entertaining error. I am. Is that like that in your book too, Kyle? Mm-hmm. Yeah, I thought that was fun. I don't know what the 1m part of this equation is.
I'd like a list for you.
Okay. Now, when we square these, we do them separately, but there's an easier way to do this, and it involves yet more math that seems kind of scary, called the complex conjugate. So I can say squaring these separately is the same thing as taking the complex conjugate of them, psi star psi. Okay, the notation gets simpler, but the math gets more difficult. And I will show you in a minute that it's not terribly difficult. This, again, gets us back to the idea that we have the square of the original wave function. Now, I keep putting the absolute value signs around this so that we end up with a positive number. This also allows us, and a real number for that matter. Okay, once we take the complex conjugate of this, we're no longer in imaginary space, which is nice. So the thing that I'm saying that really does matter, the intensity and the actual probability density of finding this, is a real equation that can produce real numbers and that no longer has I. Problem is, we have to have a wave function that has I to get to here. Okay? So we'll practice that. Okay. All right, so let's say my wave function looks something like this, and I say, all right, I want some length delta. I want to know what is the likelihood of the particle being in this space. All right, where is the likelihood of that? Well, the problem is that's we're going to have a probability per length. What did I miss?
All my classes are coming together in this one class.
Oh, really?
I did probability too,
They're all merging.
Yeah.
It should make it easier, right?
At least you know how these things are.
So calc-based physics, there's a lot of students are taking Calc 2 at the same time. And so I've been talking to Dr. Lee. It's supposed to time such that when you start to get to integrals, it's the first time you use integrals in physics. It would be nice if everything worked well together.
But we rarely use integrals in calculus.
Yes, we don't use it. Well, wait, you had Hamilton, right?
I had you for everything. I had Simmons for physics 1, and then you would.
Right. And none of you had Edwin for 2200. Right. I used them. I liked
I
them.
had you for math. I had you for physics 4000.
Yeah, I remember that. And we did do some integrals for it.
Like 1.
You use them a little bit. It's just not like whenever you want to take the work, you have to integrate the force.
Yeah.
Or anytime any area under the curve, you take
We
some
did that.
integrals. So.
Yeah.
But you had Simmons, so that makes sense that you did do that. And then the ketchup stuff, I mainly taught you guys topics.
Is that how we went back and forth from velocity and acceleration too?
Yes, you can move. Yeah.
I think that's what we did.
Okay. So this, in a one-dimensional space, we're going to say, what is the likelihood of finding a particle in this location? It's going to be probability per length. Now, very quickly, if we want to start talking about real things, we're going to have to talk about three-dimensional space. So then it becomes probability per volume. Okay, that we're going to likely find a particle. That's why this is called a probability density. So that weird term is because it's per volume. Anytime you have density. So when we talk about density originally, we always think of mass density. And it really should be said that way. Mass per volume. let's think about some other things that's given per volume. Alcohol per volume.
Moles.
Moles. Yeah, sometimes you get per volume on that. Why can't what other kind of densities do we deal with?
Molarity.
Yeah, not chemistry. There's all sorts of densities. We have electron density. Jeez, I just think 2212 stuff. Electron density, the number of electrons in a given space. So that's just a number density if you want. And we do use number density both in chemistry and around. Anything per volume is a density. And we even sometimes do it per length. We would do, coulombs per length, and that would be per area, but you could still call it a density. All right, only point is that's where the phrase comes from. It's a probability function and has to be given over a chunk of volume or length. All right, away that goes. Now, let's start to handle this monster. All right, let's turn our attention to the plane wave. Plane wave. Do you guys know what a plane wave is?
You can show us.
What?
You can show us. We might know what it is.
Yeah, it's really hard to freaking draw, but okay, I will try to draw it. Draw it like this, and you think of it as, okay, it's a giant wave that's coming at,
Okay.
let's see it like that. I can't really draw, but it basically it's one giant wall coming at.
So it's kind of like if you have a blanket and you just flip it like
Perfect.
this.
Right. So that would be a plane wave that's coming straight at you. Now, in general, it's really freaking hard to create plane waves. In optics, we'll talk about them all the time because it's very useful to create plane waves, and there's ways to approximate a plane wave, but you can't have an infinite flat wave that's really coming
So
at
is it like we were zoom in on the circular waves?
Sure, exactly. And anytime when we also talk about double slit, if you guys remember that, we say that we have an infinite plane wave that's coming at it like this, and then we have a circular wave that came out the other side. We assume that it's an infinite plane wave just because it makes everything easier mathematically. All right, so that's what we're going to start with. Let's start with the simplest case of a wave, which would be the plane wave. If we have this, one solution then for a wave function of a plane wave will give us A, E, I, kx minus omega t. We now have a wave function. Predicts this. Now, this is not terribly different than the wave function that we use for just particles on a string. Now, this is just particles in existence. Let's describe that. Now, if we want to know this, then the way we have to figure this out is if the wave function is, in fact, a solution to the wave equation, the easiest way to do this is just to plug it into the wave equation and see if it works. This is where the math gets ugly, and Kyle, don't get too scared. It'll be okay. I will hold your hand. It'll be okay.
Kyle,
make it do this. David, hold his hand while we do this.
I'm scared too.
Don't touch me.
All right. So now we're going to solve both sides of this. So let's start on the left side.
I like the book better. It just says magic, and then you get this.
Imagine that. All right. So I just assume that everybody remembers how to do double derivatives, and we'll skip right over this solving it out part on the board. If you want to go the magic approach, I'm fine with that. I just imagine homework might be.
Friendship is magic.
Oh, God.
What?
Double derivatives are
I
not
love
bad.
double
This
derivatives.
has done it so long.
All right. Well, that's what we're going to practice then. And I was doing this mostly, Kyle feel better, but he's the one who doesn't want to do them, so we'll just skip it. We'll just assume we're all experts.
Like accept the C for this entire course and be done.
You make it D minus. I'll take D minus right now.
I'd rather have the C so I can actually go places.
I was going to say, you have to count this. Anything under C doesn't count probably for you, right?
No, I probably get a D in this course. It's not part of my actual degree, but probably wouldn't look so great when you go to apply.
Is that a KX or an EX?
No. What?
The AE thing? Get AE, I.
A-E-I-O. Okay. KX minus WT. Yes, omega t. All right. We're going to take the second derivative of this.
Okay.
Now, this is going to be ugly because this is going to look like this. What number does that equal? goal. All right, let's back up and let's just deal with some simple derivatives. Let us remind ourselves of some things that we already know. E to the x. If you'll notice here, that's what I have. I have an e to the I x, but x gets a lot more complicated. What is, by e to the x, what can I say that the derivative, the full derivative of e to the x is equal to? E to the x. E to the x is awesome like that, and it's nice and simple. All right. Now, what would I say is the partial derivative of e to the x equal to?
It's not E to the
It is e to the x.
Okay.
E to the x. Okay. So, what is the difference between a partial and a full derivative?
It's split out based on the components.
Yes, and you only have to deal with the components. We will be dealing, this is a really good thing, partial derivatives might look scary to you, but I assure you they're much easier. When I take the partial derivative of this ugliness with respect to x, I can ignore all of this, the omega t. That is very handy. Even if t is a function of x, which it is, we know that, the time and x are interrelated. But if we're taking the partial derivative, it just magically goes away. That's handy. So let me show you an example where it would have mattered. If I want to take d to the dx of xy, what is this equal to?
X. Oh, wait.
No, it's not.
No. No.
Is this a partial derivative?
This is a full derivative.
Full.
And can you guys tell the difference now between my partials and full?
Kind of.
My fulls have tails. So in the way that I write it, you can see it this way. That's my full. This is my partial.
Okay.
So you won't see this part down here for my full.
Oh, it's y prime plus x times x.
Is this a
No,
change?
isn't it like x prime y plus x y prime or something like that? Like
look
the-
at your
the
primes.
prime to be
Depends on-
derivative.
Okay, your prime's being derivative.
Yeah.
So we're going to take the derivative with respect to x of this. So this is going to be y,
X plus y.
and then it's going to be times dy dx.
Yeah.
Because the partial, and instead, if we took this as the partial derivative, so the partial derivative with respect to x of xy, this is just equals y, which is lovely. Okay, x just goes away. But in the event, we don't know if dy dx changes. Now, in the event that there's no change of dy dx, what does this equal? 0?
Sure.
No, the answer is 1. Because it's going to say that the same change in y is going to be equal to x. It's not going to go to 0, it's going to go to 1, so that we end up in here. There is no respective change from one to the other. Okay, so that's a little review on partial and full derivatives. Fortunately, we only have to deal with partial. So next question over here. The partial derivative du dx of e to the 2x is equal to what?
2e to the
2e to the 2x. So we still just get that back. All right, good. Hopefully we're remembering this. We're going to be taking a lot of derivatives of exponentials in here. So now if we go up here, I'm going to show you that this really isn't nearly as complicated as you might think. If I take the partial derivative of this, first of all of this junk still stays out front. And you can tell because I've already even skipped by it by putting the derivative on the inside here. Now the derivative of aei to the kx minus omega t, the only part that we care about is right here. So I want to take the first derivative of that, and what am I going to get?
I, K, e to the...
ik, and then the whole damn thing back again. So let's take this now. Let's look down here. One last example. What if I had d squared dx squared of e to the 2x? What would my solution be?
4e to the 6.
4 to the 2x. Okay.
Oh, and then there's two i's that may make it negative.
It's got to be real handy like that.
Yeah.
So this is actually kind of nice because, like I said, we're going to end up getting rid of the our imaginary part. So over here, I'm just going to put ik squared multiplied back by my sine function. Actually, I'll write it out first so that it makes a little bit more sense. So then I end up with aei to the kx minus omega t. Okay. Now, if I square this, I'm going to end up with a negative 1, and I'm going to have k. So I'm going to end up with a positive h bar squared, k squared over 2m. And this is just my original wave function that I had in the first place. Psi x of t. So taking the second derivative of all this really just got us out a negative k squared. That's the only thing that really happened, because the I went away. So, not so bad. All right, so now I'm going to erase all this, assuming that we understand what's going on here.
I like this so much better than special relativity.
You like what?
I like this so much better than special relativity.
Oh,
Yes.
really? Nice. See, I love special relativity. This stuff's okay to me, but special relativity is concrete. I mean,
Can I
it's
just go back
really
to
cool
algebra
at
based?
this. What?
Can I just go back to algebra based?
Dr. Ross, I'll give this much to you. I like this better than the first time I saw it for you.
Should we get to know my excuse for being late?
Let's-
Late today at 2:30.
All right, now let's talk about the right side. The right side of this equation over here. I h bar d, the derivative of this. Now this is only the single derivative, but it's with respect to time. We can do this a little bit faster. Now, if we're interested in the t part of this, the time derivative, then we're only going to be looking at this section over here. Keep in mind, we can't ignore that I, because that I will multiply through though. So if we have I h bar t times, let's write it out. We're all divided by our partial derivative with respect to time. The only thing that's going to come out of this is an I omega. Okay? But it's going to be a negative I omega. So we will end up with I h bar negative I omega times our psi function back. Same thing we already had. So we multiply through, and we end up with a negative i's that kind of go away. We end up with a negative I squared, which is a negative 1. Get a positive number back, and we get hw times x of t. So we end up with h bar w psi x of t. Why have that set? The right side. Anytime anybody says left side or right side, I always think back to remember the Titans with Denzel Washington. Wrong side. And that movie was, it was like one of my first TVs that I watched that thing over and over again.
Good movie.
Yeah, I like the run when he runs out to Gettysburg and whatnot. Wow, that's cool. All right. Sure. Now what? Yeah, what the heck does this tell us? These questions.
Man, I think that's the particle beyond. I have no idea.
So we have this two sides before
We have two sides of the equation, so now we gotta deal with it. We've got hk squared over 2m times psi, and we're questioning whether or not this is going to be equal to our h omega psi. Does this or does this not work? Well, we can cancel one of these, so I'm going to space this out. Look at that, just by removing the parentheses. That's the right way. That worked out well. So, and we can cancel this. Yeah, and then we're going to I kind of like that. So I can say that if this is true, omega needs to equal k squared over 2m. Okay. Is that true or isn't that true? I don't know. Well, let's go back and check what our original function is.
I have a question.
Yeah.
Okay. Why is it h squared over there, but it's just h over here? And wait, what? Doesn't that leave us with 1h still?
Because I magically, it does leave us with 1h. I
Yeah.
magically, oh, yeah, right up here.
Okay.
I magically math just by removing parentheses.
Okay, I was just confused at the h something.
No, you're right, Alright, so that's why I left this up here for the stuff that we did last time, because now that we have these wave particle relations, let's throw them in here and see what we get. So for our omega here, we're going to have E over H. So I'm going to have E over H bar. When I say H, just know that I mean H bar. And for K, I'm going to have momentum over H bar. So momentum H bar over H bar. And actually I'm going to have H bar over H bar squared. Oops. So I need to have this as P squared over H bar squared. And I'm still going to end up with a 2m. Alright, this H cancels with this H cancels with the other H. We end up with the grand equation E equals P squared over 2m. Anybody recognize that yet?
Yeah. Is that in? That's an actual equation.
Or what is P squared over 2m though? We talked about this go. It is kinetic.
Is it kinetic?
Now I'll show you, I'm going to write it out. This is the more traditional way that physicists write kinetic energy. Now, it's not introduced this way because it's slightly more confusing to students, but anytime you're dealing with quantum theory, you're always going to deal with momentum. You'll see momentum more. So if I write this out, this is m squared v squared over what I end up with 2m. The m cancels, I end up with 1/2 v squared. It's the exact same thing.
I'm going to stick that right.
So, the question goes back is, well, we still haven't answered everything. I postulated that here's a wave function that will work for our Schrodinger's wave equation, which we believe to be true because I told you to believe it. And we said, is this in fact a solution? Okay, that solution, working all that out, said it is a solution if and only if this is true for these constants. Working these constants out, we found out, well, that means that that is true if the energy is equal to 1/2 mv squared. Now we know A energy is equal to E equals 1/2 mv squared, but that's saying that the total energy of the particle, now it's the total energy of mechanical energy. Now this is a point, because we're only looking at the particle's location, all right, and its likelihood to be someplace. Now that's dependent on its total mechanical energy, which means its total potential energy and its total kinetic energy. So we're not talking about rest energy here. Rest energy doesn't matter. But this is saying that the total energy is just equal to the kinetic energy. Any ideas why? Why not potential energy?
Is the particle moving, so it's not really have potential energy?
It's because it has the same potential. Is it where?
No, not necessarily. It's because there is no such thing as potential energy at the point of just dealing with a single particle. If we are looking at just a single particle, is that what you're going to say?
I was going to say, isn't there like, is it because there's like essentially no mass and the whole thing is moving or something along those lines?
No, not necessarily. The particle definitely just had mass, we still have it. But it's the idea that we're dealing with a single particle. We're not talking about a lattice or something like that, where the particle can have spring potential energy or anything like that. We're talking about the location of a single particle. And a single particle, the only type of energy it can possibly have is kinetic energy. It in and of itself cannot create potential energy. We're not including anything else right now. We're just looking at the one particle. Not to mention other potential energies would be dominated by gravitational fields, which have their own set of equations, E&M fields, which have their own set of equations. We're just saying we just want a particle to exist in the middle of nowhere. So there is no potential energy. The only energy we could possibly have is the kinetic energy. So this is, in fact, a possible solution for this. One solution to the Schrodinger equation. Now, let's go back and let's figure out the probability density. Now, we do have one function. It solves this. It works. Great. You have to do all of that just to prove that it's even a possible candidate. Now the question becomes, all right, it's a possible candidate. What is the probability density? To do that, you okay?
Just bang my leg off the desk.
Heard that. To do that, we have to do psi star psi to figure out what the probability density is. Now, this is not bad. If you guys follow, once you understand this, it'll be easy. Ready for all the crazy math?
Sure.
A minus I. That was hard. To take the complex conjugate of something, all you do is switch the i's to the negative or whatever they were. So if they were negative, they become positive. Okay. I, kx minus omega t. And I will draw on something else. Let's look at an example. E to the 2x times e to the minus 2x. What does this equal? end up with this equals e to the 0. Anything to the 0th power equals 1. Ah, handy, right?
I remember that.
Okay, so e to the negative I, e to the I, what is my answer going to be here?
A squared.
A squared. No, I was waiting for someone to say 1. No, a squared. All right, so my probability density, my psi star psi, is equal to a squared, is my intensity. Now, but it's just a squared. It's just a constant. So what does that even mean? That it's equal to a squared. It's not a function. The intensity of this function comes back as just a constant.
Is that probability density?
Probability density comes back just as a constant. Do we care? Is that a concern?
Yeah, because it's saying that the probability of everything is the same, right?
Yes. So why is that okay?
Because everything in the universe is to balance out?
No, this is just for one example. What was the example that we were doing this for?
Plane wave.
A plane wave, which is freaking straight right across the top. So there's no likelihood that it's going to be any other one location than any other location, because it's just coming at you as one giant plane wave. So wherever the amplitude is, I don't care if it's halfway, it's identically halfway all the way across. The probability of it being anywhere in that plane wave is identical. So this just comes back to a squared.
Okay.
The same. Now, when we start to deal with more complex functions for our wave function, then we're not going to get a squared. We're going to get something back that's a function that says, hey, it's actually more likely to be in this chunk of the wave than the other chunk of the wave.
Honestly, I forgot we were doing a plane wave. Or the wave
Well-
is still relevant.
Remember,
So would reading this book actually help me at all when I build schools as I do?
now, that's what I wanted to talk to you guys about. I also have a couple other books, and I forgot to bring them. I was going to bring them with you. Now we're at the point that reading one textbook, and this usually happens just about any other level physics course, may or may not be enough. So one of the recommendations I have is your PCAM book that you have is actually quite good. It's big and scary,
The red
but
one
if
or
you can
the
find the sections in it. It's a giant red book, or at least my version of it's red.
yeah,
I also have two other modern textbooks. If you're interested, you're more than welcome to stop by. I will show them to you. You can even check them out if you want. I don't want anybody looking at it for more than 24 hours, but I can log them to other people. But our library has a couple examples too. What I don't recommend you do, and I wish somebody would have told me this when I went to school, don't sit there and read the same thing, go, I don't get it, and then just read it 12 more times and not get it 12 more times. It's not going to help you. This is the one time where the library or borrowing a book from me really will help. Read the same thing just from a different point of view, and sometimes it can be two words that are just switched, and all of a sudden it all makes sense.
so if we bring the red book, will you show us what?
Yeah, I don't remember where the sections are, but I'll help find the sections in there for you. So that's all I've got today. You guys have one homework problem.
So, what are we supposed to read about?
I'm just saying in general moving
Oh,
forward.
okay.
Just in general moving forward.
The red book is purely
You guys have